In this introductory video, we're going to be looking at some of the historical developments behind organic chemistry, what's its significance to society, and then a few details about chemical bonding in general that applies more specifically to organic compounds. Okay, so organic chemistry is the study of carbon-based compounds. You may be wondering, if there's all these elements in the periodic table, why do we have two courses devoted to just one element? Okay, well, the reason is that carbon forms very strong bonds with itself and virtually every other element except the noble gases, and carbon engages in three different bond types with those elements, so the number of combinations that can give rise to stable compounds really approaches infinity. Okay, just to give you an idea of the importance of organic compounds, let's go back about 30 years before computers, or before, we had computers, we didn't have internet really 30 years ago, but let's look at how we used to search for things. Okay, every 5 years, the American Chemical Society would publish something called the Chemical Abstracts Collective Index. And one of the most useful ones there was the Formula Index, which would just start from A, which is the first element in the alphabet is actinium, and go all the way to zirconium in about 25 or so volumes. Okay, if you look at how these volumes were arranged, the first volume would be the compounds with actinium up to compounds that had 3 carbons. So this would be volume 1 right here. All right. Then we would go through several volumes where there was nothing but carbons. It would be like C3 to C5, C5 to C6. There'd be some other elements in there as well. And then at the end, you'd go from something like 32 carbons to zirconium. All right. So if you look at this little graph here, this tells you that almost all the compounds known are organic compounds, okay? And that's why we have such a huge emphasis on organic chemistry. There's more compounds that are organic than not organic, far more. Okay, if you want to look at where are the inorganic compounds, totally inorganic compounds, they're only right here. That small set of the periodic table there, and the small set or the collective index right here. And right here are the organic compounds. Okay, so we see that. So this gives us a real idea of the importance of carbon-based compounds. All right, now what about the word organic? That implies wholesomeness, things coming from nature without any human alterations or whatever. Well, in this definition, it's very different from that. All that organic means is that it's derived now it means that it's carbon-based, but in the old days, we'll say 1850, we had two types of chemists that dealt with the study of matter. We had inorganic chemists who studied rocks, minerals, and compounds derived from them. Most of their compounds were crystalline. They had no volatility, had extremely high melting points. Often they were colored. Whereas organic chemists would study compounds that were derived from living sources or from sources that used to be living, like oil and coal. Okay, and these compounds were often liquids or meltable solids. They often had odors, and they usually were either colorless or yellow. All right, so in the early days, people in these two fields thought they were studying different fields. They never talked to each other because they didn't use the same techniques to characterize their matter or the types of things they studied had no resemblance to each other. Okay, But the techniques of organic chemistry and organic chemists were thus very different back then. All right, a very significant experiment in the 19th century was this experiment by Wohler, where he took an inorganic compound, ammonium cyanate, and turned it into an organic compound, urea, okay, which is the major non-aqueous ingredient in pee or urine. Okay, so that's ammonium cyanate, and this converts to urea. Recognize that if you take their formulas, it's actually identical formulas, so we're just transforming one form of CH4 into O into another compound of the same formula. All right, since this time, organic chemists and inorganic chemists realize that they are the same types of chemists. They study the same thing. Okay, it turns out that their compounds come out looking a little different, but as far as the raw pictures of bonding and structure and the looking at molecules, one molecule at a time, we're really two iterations of the same type of chemist. And now the organic chemist spends more time probably talking to the inorganic chemist than any other type of chemist. Okay, organic chemistry has had a major impact on life as we know it. Many important developments. You might argue that they're not, that they've caused more problems than they have, but the thing to note is that our life today is a lot better than the life of a person in the 19th century, and much of that is due to advances in organic chemistry or advances made by organic chemists. All right, so let's take a few examples. There's nutrition and the food supply. We've isolated and characterized and prepared virtually every substance required in our diet. As far as crop protection goes, advances in the manufacture of fertilizers and pesticides have revolutionized agriculture to the point where only 2% of Americans are needed to feed us. And I think if you look at in the 19th century, more than 50% of the people were employed in food production. All right. Medicine. More than 95% of all prescribed and over-the-counter medicines are described as unnatural organic compounds. They were designed by biologists and chemists working together. They were synthesized by the chemist, and to turn that synthesis into a batch scale, large scale synthesis that can supply millions of people, we need the help of chemical engineers to scale it up. Okay. Important advances in antibiotics, anti-cancer drugs, antifungals, and anti-inflammatories have made great improvements in our lives. Our life expectancy approaches 80 years now instead of 40 years. Okay, and most of us don't worry about an acute infection killing us. There are a few that can, but the number of them that are out there are much fewer than they were 100 years ago. Okay, we've also added many luxuries in our life. Gasoline, natural gas, coal, ethanol, biomass, these are all organic compounds, and the techniques of organic chemistry have been used to purify and reformulate them so that their side effects like pollution and whatever are minimal. Okay, we've also made a lot of advance in materials. Many of the materials that we see in our life are synthetics. Many of the fabrics like nylon, polyester, rayon, orlan, spandex are totally synthetic compounds derived from petroleum for the most part. Other useful materials derived from petroleum that are not fabrics include polyvinyl chloride, which is used in pipe construction, polyethylene used in trash bags and various containers, and polycarbonates, which are also used as containers and lenses, are all organic compounds. Organic chemistry leads to a better, knowledge of organic chemistry leads to a deeper knowledge of how biological systems operate. We can look at biological systems as being a series of interactions or chemical transformations involving primarily organic compounds. All right, there's a few negatives associated with organic chemistry. Organism resistance from overuse of pesticides and antibiotics come to mind. A lot of new substances turn out to be carcinogenic. This is because while we can test the short-term effects of most new substance, it's hard to test what it's going to do over a 30-year span. And some of the chemicals that we've talked about previously do have can be abused in some ways. But overall, I always give this argument. A lot of people who hate chemists think of dream of an ideal world that has about 500,000 people in it, but most of them don't realize that their fate would more likely be the ones who were never born than one of the ones enjoying this idyllic lifestyle, this earthly paradise. Okay, so it all depends on how you view that. But anyway, we don't get good press, organic chemists. We're important in all of these things, but we often are kind of in the more in the introductory process phase than actually the true discovery. Or we're not the ones that usually you look at, but they couldn't be made without us. Like if you look in the media, I can't think of but a couple of people or a couple of movie and TV characters that are organic chemists, and neither of them are considered positive role models. Okay, Clark Griswold, he never came out and said he was an organic chemist, just that he was a genius with food additives. Okay, so I assume that he must have been an organic chemist. Walter White here, he's a fellow New Mexican. He's a chemical educator, but he became rich by practicing organic chemistry, taking simple organic compounds and turning them into methamphetamine. Okay, and that if you know the TV show Breaking Bad, that's the whole theme of that show there. So that's an example of, I guess, abuse of organic chemistry. All right, let's look at chemical bonding. There are 2 to 3 bonding types, depending on how you classify the third bonding type that are important in organic chemistry. Okay, chemical bonds are driven by the desire to achieve a Nobel gas configuration and the maximum number of bonds. Bonds are stabilizing. Okay, we're going to talk about bond breaking and bond making, but one thing you'll realize from these discussions ahead is that virtually every case I know of where a bond is broken is a endothermic or energetically unfavorable process. You have to put energy into the system to make a bond break. So bond making is stabilizing, bond breaking is destabilizing. All right, bond type number 1 is ionic. This is between 2 atoms with extreme electronegativity difference. Often these are on opposite columns of the periodic table. Okay. At the other extreme is covalent bonding. This is between 2 atoms that have similar electronegativity and they're sharing their electrons. We'll see that when we look at some Lewis structure diagrams on the next slide. And the third type, it may not, I don't know if it's really worth calling this a different type of bond, but it's sort of an halfway between the bond type 1 and bond type 2 there, and this is called polar covalent. This is between two atoms with different significant electronegativity differences, but they're not so different that they're going to be classified as ionic. They're pretty much covalent bonds. All right, so let's look at bonding from a Lewis dot structure sense. And this is useful. It'll show us how bonds are distributed or how electrons are distributed in bonds. Okay, let me just say one other thing about bonding types here. In organic chemistry, covalent and polar covalent are overwhelmingly the most important. This is because carbon is in the middle of the periodic table and doesn't readily engage in ionic bonding all that well. Okay, so here's an ionic bond. All right, so what we're going to do here is we're just going to transfer this electron at sodium, and we're going to move it to chlorine. Okay, I've made the sodium electron magenta and the chlorine electrons black, but you can't really label electrons that I know of. Okay. All right, so here we're left with two species that have a noble gas configuration. Sodium plus has the same configuration as neon. Cl minus has the same electron configuration as argon. Although we're not really drawing any bond here, these are attracted to each other, of course, because a positive charge is attracted to a negative charge. Okay, so this is our bond, the attraction of a positive charge to a negative charge. Examples are sodium chloride, lithium fluoride, KOH, i.e. the potassium-oxygen bond, and magnesium bromide. Ionic compounds, they tend to have very high boiling points and are usually solids due to a complex network of ionic attractions. They also tend to have very high water solubility. Water is a polar compound, and ionic compounds themselves are very polar, so they have similar characteristics, and they dissolve and they mix well with water. Okay, in covalent bonds, here we're using elements that have identical electronegativity because they're, in these first three cases, of course, they're identical elements. And we're going to consider the carbon-hydrogen bond as being pretty close to being purely covalent. The electronegativity between carbon and hydrogen isn't great. All right, so what we're going to see here is that we're not transferring the electron from one species to the other. We're getting the species close to each other, and they are sharing their electrons. Okay? The electrons that are in the bond, which are these two right here, these are being shared by the two elements. So, but what we can see is that each fluorine here has some sharing arrangement in 8 electrons. 8 is the magical Nobel gas configuration. All right, so this bonding electron pair, the structures get a little bit cluttered when you draw all these electrons. So a bonding electron pair will often be represented just by a single line, and when it is written this way, this is going to be referred to as a Kekule structure. The line between the elements implies a 2-electron bond. Okay, here's methane. All right, so carbon has 4 electrons, hydrogen has 1. We can take 4 of these hydrogens and have them interact with the electrons at carbon. We end up with 4 bonds, 4 electron pair shares right there. Okay. And this again achieves the Nobel gas configuration. Hydrogen has 2 electrons, so it's just like helium, and carbon has 8 electrons, so it's just like neon, 8 valence electrons. Methane, remember the structure. It's the simplest organic molecule. All right, here's a polar covalent bond. Hydrogen fluoride is a very good example here. All right, so we're going to take the hydrogen and its electrons, but we're going to get them together close and have it shared predominantly. But in the sharing arrangement, I don't know if I've shown it very well here, the electrons are more attracted to fluorine because it has a higher electronegativity than hydrogen. Thus, this puts what we call a partial positive. This just means partial at hydrogen and a partial negative at fluorine because, again, of the 8 electrons that are buzzing around hydrogen and fluorine, or the valence electrons, they're spending more time at fluorine than they are at hydrogen. This creates a bond dipole, which is notated by this symbol right here. The symbol that looks kind of like a positive charge. This is called the positive end of the dipole. And this end with the arrowhead is called the negative end. Okay. All right. In the vast majority of organic compounds, covalent and polar covalent bonds are the only types of bonds. Okay. A quantity known as bond dissociation energy, which we're going to take up in more detail in Chapter 4, is defined as delta H for the what we call the homolytic bond cleavage. Okay, that's breaking the bond and have one electron go to one atom and the other electron go to the other atom. This reaction is always endothermic, it's unfavorable, and the higher the number for the bond dissociation energy, the stronger the bond. It's a term that we use a lot in this class, so often that we're going to abbreviate it as just the BDE. All right, so we're going to look at this problem right here. Classify each bond as covalent, ionic, or polar covalent. And this is a type of, this is the way this course is organized. Problems are interspersed into the lecture. Because you're looking at this on the internet, what you want to do now is pause this, try to do this problem yourself. You don't necessarily have to write it out, but try to do it in your head and anticipate what the answer is. I'm going to just go right into the answer, but you have the ability to pause it and try it yourself, and that's the best way to succeed in this class. All right, the CH bond is covalent, very slightly polar. I think the electronegativity difference between, I think carbon is 2.5, hydrogen is 2.1, so there's not an appreciable electronegativity difference. The oxygen-potassium bond is ionic. Okay, these are a very electronegative atom, oxygen, bonding to a very non-electronegative or electropositive element, potassium. And finally, the CO bond is a polar covalent bond. There's an appreciable electronegativity difference between carbon and oxygen, but not so much that we would ever consider this bond to be ionic. Okay, let's look at Lewis structures when we have multiple bonding situations. All the other ones had single bonds. Okay. All right, so let's draw formaldehyde. I'll just name each of these. Okay, got to spell them right. All right, so this has an oxygen and 2 hydrogens surrounding carbon as a central atom. So let's just look at each element with its maximum number of unpaired electrons. We have hydrogen with 1, carbon with 4, and oxygen with 2 unpaired electrons and 2 lone pairs that we really can't use for bonding purposes. Okay, when we pair them up like we did before, we're going to end up with this structure right here, but if you'll notice in this circle, I have 2 electrons that are not part of the bonding scheme, and neither carbon nor oxygen has an octet here because if you count the electrons that each has a share in, it's only 7, it's not 8. So what we can go ahead and do is make a second bond between carbon and oxygen. Okay, and this is called a double bond. All right, so this is the structure of formaldehyde right here on the right. Carbon-oxygen double bond, 2 lone pairs at oxygen. Okay, all right, let's look at this one, which is called ethylene. All right, in ethylene, we're going to have 2 carbons, so we're going to have a carbon-carbon bond, and we're going to surround each carbon with 2 hydrogens. All right, so we can achieve the 8 electron or Nobel gas configuration by making a carbon-carbon double bond, and this is the structure of ethylene on the far right over here. All right, we can go even further. So this molecule is kind of a very toxic molecule, hydrogen cyanide, but it's our simplest compound that has a triple bond. Okay, so let's see how we can arrange carbon, nitrogen, and hydrogen into a compound that has octets for, or a Nobel gas configuration for everybody. So here's carbon with its 4 unpaired electrons. Nitrogen would have 3 and a lone pair. All right, so we're going to make our single bond here like we had done in the previous slides, but this leaves us now with 2 of these sets of unpaired electrons. Carbon and nitrogen in this configuration each only has shares in 6 electrons. They want 8, so we're going to pair up both of them, and now we're going to have a triple bond. Okay, 6 electrons shared between 2 atoms. Okay, and the final structure of hydrogen cyanide is the one on the far right, again with a carbon-nitrogen triple bond and lone pair at nitrogen. Both the carbon and the nitrogen now have 8 electrons. Carbon all from the 4 bonds, nitrogen from 3 bonds and a lone pair. Okay, this is as far as it goes in organic chemistry. We don't have anything more exotic than a triple bond in organic chemistry. Okay. All right, let's look at the effect of degree of bonding on bond strength and bond length. As the bonds, degree of bonding gets more and more, okay, we'll just name these as we come to them. Ethane, ethylene, acetylene. All right. As the degree of bonding gets higher, the bond gets shorter. Notice ethane, it's 1.54. Ethylene, it's a little bit shorter at 1.34, and acetylene, it's much shorter at 1.2. Okay. There's some effects on the CH bonds, but we'll get to those when we talk about compounds that have double bonds and triple bonds. All right, look what's happening to the bond dissociation energy. It's 375 there, 720 now for the double bond, and 961 for the triple bond. Note that 375 times 2 is actually 750. It's not twice as strong, and we're going to use that as evidence that our second bond isn't as strong as our first, and that's going to be a big part of the reactivity picture for compounds that have carbon-carbon double bonds in chapter 6. Okay, so we're going to end this video by just drawing Kekule structures, including lone pairs for each species. All right, so the first species, we're going to just assume that they are drawn in the same order that I have written here, so we can sort of figure out what's the central atom or who's bonded to who. What we're looking at in this problem is what the degree of bonding is. All right, so this first one, we can get octets for nitrogen and oxygen with this bonding arrangement here. Nitrogen-oxygen double bond, 2 lone pairs at oxygen, 1 lone pair at nitrogen. This molecule here, which is called cyanamide. Okay, we can again just draw the following Kekule structure here that would have the right number of lone pairs and bonds to give all of the carbons and nitrogens shares in 8 electrons. Okay, this third one, this is the only arrangement we can have here. Carbon nitrogen double bond gives us octet carbon, and then if we look at the nitrogens, each nitrogen has 3 bonds and a lone pair. That gives us the octet at nitrogen. And this molecule here, recognized, has something that we call symmetry. It's a symmetrical molecule. Everything on the left side of that slash mark looks like the right side of the slash mark. Or you could pretend that this slash here is a mirror and that it's just looking at a mirror image of itself. Okay, this last molecule, I think it's called ketene. It's not really a stable molecule, but we can achieve the Nobel gas configuration for all the carbons and oxygens with this arrangement here. Carbon-carbon double bond, carbon-oxygen double bond, and 2 lone pairs at oxygen. All right, so in the next few slides, we're going to look at how we can sort of expect or how atoms look in their normal valence state and what happens when they don't look like their normal valence state. You may have noticed that all of my nitrogens have 3 bonds and a lone pair. All my oxygens have 2 bonds and 2 lone pairs. All the carbons have 4 bonds and no lone pairs. And that's what we call the normal valence state. And we'll look at that in more detail in the next few slides. So this one's going to end right here.